everyone, welcome to day 2 and session 3. So just as a start for the people in the room, I think there's maybe 1 or 2 who weren't here yesterday. Your board's in front of you. If you want to answer a question, you just turn it vertically. And yeah, Piers is ECMWF. So we're just going to start with a bit about this quite grand council chamber that we are in. So I'm going to hand over to Carlo, who's going to tell us a bit about the history.
Hello, good morning, everyone. Nice to see you here today. Yesterday, we jumped straight into the different task team discussion. So I really didn't have an opportunity to say hello and welcome to ECNWF. And so I thought of doing so this morning. It won't take me more than a couple of minutes, but just to say hello and great to have you here. And without spending too much time, just to say that ECNWF is an international organization, is not a EU organization, so our member states do not coincide with those of the European Union. And these flags here are not just a part of the declaration, actually represent our member state on this side and our cooperating state on the other side. And as you see, there are several flags that are not part of the EU. And this is the place where at least once a year, often twice a year, our member states sit down and make decisions. So this is our little parliament, if you want, is the core of our ECNWF works, and all the decisions need to be ratified and supported by member state. The fact that it is not a EU organization, but actually an international organization, also means that the agreement has been ratified by all the parliament of the all member state, meaning that any sort of substantial change in our status will require changes approved by all parliament states. So it's a very solid and slowly moving organization, if you want. At the same time, we have been doing weather forecast since the mid-70s. Actually, next year we will celebrate our 50th anniversary. So there will be some publication and high-profile event around that. And over the last 10 years, we have been working more actively on climate with the Copernicus Climate Change Service that I have the luxury or the responsibility of leading on. So nothing more to say, just welcome. Very important for us to host you here, and looking forward to the rest of our chatting and today, tomorrow, and on Thursday. Thank you.
Thank you, Carlo. It's great to be here. And so today we have this on the agenda. We'll talk about models. Models in relation to 4 things. First, we'll start off with status of V0 data implementation in the models, summary of the DECK experimental protocol in CMIP6 to motivate discussion on what we should be doing for CMIP7, and then revisiting the PyControl scenario map protocol with about 4 or 5 talks lined up, with 1 recorded talk by John Fasulo. And then, of course, discussions on the development of protocol that could then be sent up to the CMIP core panel for approval. All right, so I'm lined up as providing a status of V0 data implementation in GFDL models. And I see that this was not updated, but that's okay. I think we pretty much have everything. So I just wanted to start off with a big thank you to the forcing data providers, not only the data providers, but also all of our team, and especially Paul, Zeb, Sasha, for getting all the data formatted correctly and all lined up and uploaded on ESGF. So at GFDL, we've started thinking about forcing data. We have, just as a task team, we have a focused subgroup on forcings as part of our model development team. We start off by obviously downloading all that data to our local data drive. And then we have a group of people whose research is kind of aligned with the different DECK forcing data sets. And so they help us with processing the data to create model ready data files and test the data to catch any issues. And then with the GitHub repo, we provide feedback that will hopefully help the data providers, and that iteration will hopefully help to update the data and get it to a final form. So in terms of running the model with these forcing data sets, I think GHGs are the only forcing that we have tested in an under development model at GFDL, our ESM 4.5, which is what we'll be contributing to CMIP7. So here it's basically just showing a 10-year by-control simulation. On your left is TREF. On your right is net radiation at the top of the atmosphere. And as you can see, the model is drifting, at least in that initial 10 years. But the key thing is the difference between blue and yellow, which is CMIP6 plus is blue, CMIP6 is yellow. And so there are very small differences in the 1850 greenhouse gas concentrations. Basically, it's methane, which is slightly different. And so that most likely causes differences in the two lines that you're seeing. But on the whole, consistent, no significant difference in the simulation. So after this, I'll basically just show some analysis plots that have been created by the different people who are looking at the data. So for volcanic forcings, we have a postdoc looking at the volcanic forcings from Tom Aubrey's group. So on the top is the difference between CMIP6 plus and CMIP6 stratospheric aerosol optical depth. The plus on the improvement that we see is that there is a clear indication of the tropopause over the satellite period in the CMIP6 plus data set, which was a problem in the last, in the CMIP6, where there was no clear definition of the tropopause, and therefore the modelers had to apply their own tropopause definition. So this is only for the satellite era, obviously for very good reasons. But going back in time, we have the full profile. There are differences in the magnitude of the eruptions or the optical depth, but in general, it seems like the CMIP6 plus is greater than CMIP6. And then I think the most important thing that has happened this time, which Tom did not highlight yesterday, but there is consistency between the SO2, volcanic SO2 emissions and optical properties, which was not very clear in CMIP6. So CMIP6 did not recommend any SO2 volcanic emissions. However, there was a data set that existed on your bottom left from Neely and Schmidt, Volcan EESM. This data set was used by one model to perform their CMIP6 simulations. And so we compared this data set with the CMIP6 plus, and we see that generally CMIP6 plus exhibits greater variability in injection heights. CMIP6 plus also includes eruptions that were missing from earlier versions of the data sets. And of course, there's more eruptions included in the post-1970 satellite era in CMIP6 plus that you heard from Tom yesterday. Land use. So overall, we see that CMIP6 plus is consistent with CMIP6, but there were some unexplained peculiarities. And so Sergey has provided some feedback on the discussions. So on the top was the area of crop and area of pastures. And in the bottom, there is the transition to pastures and transition from pastures. And that the difference here, the globally integrated transition rates among the different land use types in CMIP6 plus we see that there is a significant difference compared to CMIP6. And the CMIP6 Plus seems to have higher rates and time variability after 1990. The spikiness after 1950 was more concerning. And so hopefully, Luis will get some feedback on that. And then this you've also already seen, biomass burning emissions. Arman, who is a Fresh Eyes contributor, has put together this quick analysis of showing that the CMIP6 Plus, of course, extends the CMIP6 emissions, covering the 1750 to 2022 period using GFIT 4.1S. CMIP6 Plus emissions are lower than those in the GFIT 5 beta, and then there is a strong interannual variability that persists in the satellite era, both in CMIP6 and as well as in CMIP6 Plus. We had some requests, file formats. There were some issues that we've highlighted on the discussions that we'll iterate on with our data providers. And then there is a request for technical documentation to better understand the data sets. So hopefully with the documentation plans in the task team, that'll help get us there. Okay, so I have two additional slides, a status update from two models. NCAR, update from Dave Lawrence. They're awaiting the SLCF data sets as that is most important for them. They have not initiated testing of available V0 data sets as yet. They're focused more right now in developing CSM3. And then, of course, their organization to pull in the data sets will begin shortly. From CSIRO, we have an update from TILO. They're focused on analyzing or finalizing their CMIP7 model configuration, and then they anticipate processing the data sets towards the end of the year. And I figured maybe we can have a quick update since UK's ESM is here, if you just wanted to say a few words on that.
Sure, yeah. We're kind of in a similar position to NCAR and CSIRO in that sense. So we have a working group similar to what you've discussed for GFDL that is up and running. Again, very much aligned to people's kind of areas of expertise. And again, I think we were waiting for, more, so we've noticed the data coming online. So hopefully we will start looking at that in the coming. So we have, sprints every couple of weeks to get together and start. A lot of it's actually updating our analysis processing code from what we had in CMIP6. So there had to actually be a lot of, technical developments on that. So that's been the main emphasis now. But yeah, so hopefully we will be following not too far behind.
Sounds good. Thank you, Jane. And so we had 30 minutes for discussion. So if there are any issues that we want to, sure.
So maybe I can say a word on ICON. So at DWD, we started a big challenge about 3 years ago, where we want to further develop the NWP model ICON, the NWP mode of ICON for the use for simulating on climate timescales. So the last 3 years, roughly, we were very busy with coupling all the necessary Earth system components, but it's running now and we get the first results. So we want to use this new model, which we call ICON XPP, for seasonal and decadal forecasts as well as for climate projections. And in September this year, a nationally funded project started for providing a CMIP7 contribution of Germany with ICON XPP as well as with some 2 models of ABI, like ABI-CM and ABI-ESM. So they are also contributing to this. And so since we are currently working with the ICON XPP, we are finding a optimum configuration for climate projections. So we still suffer, of course, from perhaps some typical problems as also other CMIP6 models suffer from, but for the tests we are doing now, we used still CMIP6 forcing. So like we haven't started yet, but the plan is that in the first year of this nationally funded project, we use it for improving the model and the configuration, and then starting in September. And as I learned yesterday, I think it's a good timing because by September, most of the forcing data will be available. But of course, we will use the time up to then to learn the new forcing data and to be familiar with them by September. Thank you.
Julie, go ahead.
Thank you. So the status at IPSL is that we have been downloading the dataset as they come. So we already have set up a technical team to upload the files as they get ready. And we file them into a big table because we want to make sure that we don't lose anything or any update. And most of our task at the moment is to identify separate subgroups to test the different forcings in the specific configurations. So as the other centers, we are not ready on our model versions yet, but we want to start testing the forcings now as we are finishing the development of the models. And so for some forcings, it requires the entire couple system. For others, we can work on separate components individually. So this is why we want to separate the forcings into subgroups. So there's going to be about 7 or 8 of them, identifying people to really scientifically and technically assess the forcing sets and then see how our models is behaving with those. The specificity of IPSL, to my understanding, is that we are developing 2 versions of models for fast track, one which will be emission driven, very close to IPSL CM6 that we prepared for CMIP6, and another one which will only be concentration driven, ready for fast track and CMIP7. And our point is to precisely assess the forcings in these 2 models at the same time. So of course, there are some experiments that make no sense in one or the other of the versions, but we plan to make use of the 2 versions of the model to really assess how the forcings are inducing mostly the historical warming and affecting the future projections in emission-driven and concentration-driven at the same time.
Thank you, Julie. We have a question online, and it's from John on background volcanic emissions from satellite period. Should we discuss that in the next session after all the talks? And since Tom is going to present on volcanic, maybe we should take the question after your talk. Is that okay? All right. So John, we'll take your question after Tom's talk as well. Zeb.
Are we doing more discussion now, or are we moving on to some? Okay, so I had a question back to all the ESM teams from the forcing providers, which is that processing all the data seems like a challenge and difficult. And so can we make this any easier? Like, things I can think of would be, is it really just documentation that you need to help you understand what am I looking at? Do you need examples of how to read the data? Just like grab these files, add them like this, don't touch those files because you'll double count, blah, blah, blah. Do you just need a better database of what data is available, what's complete, what's latest, what's been retracted, something else? Like, I don't think we have great visibility apart from Vaishali about what would actually make modelers' lives easier in terms of downloading data and processing it. And there might be some easy wins.
So they hear from me quite a lot, so it'd be nice to get other modelers to chime in.
I can try. Yeah, I mean, I think documentation and information is never a bad thing. I know it puts pressure on people to provide the documentation. I think the one thing from our perspective is a little bit more, it's exactly not clear. I guess the level of versioning can get quite complicated. So obviously for you guys working on the data, it's very clear. But even in the last couple of days, we've been talking about V0 data sets. We've been talking about CMIP6+. And then when you actually go and you look on the forcing data page, you version 4.4.1. So I think, recognizing that we were only doing this in, we put a concerted effort, for given CMIP cycles. We're not maybe as familiar with a lot of those versioning systems. So maybe a bit of clarity around or documentation, just basic, simple in terms of what the versioning is. I think the request on the formatting is, as long as it's not different from CMIP6, we can probably handle that. Most of us are kind of just picking up from where we left off at CMIP6, so that should be largely okay. And I think a lot of the effort from our experience is just understanding the scientific data sets between the forcing data. So it's kind of less technical once we're up and running, and it's more kind of then it's time spent trying to understand differences where, if and where there are differences.
So maybe to add, so what I also learned yesterday is the uncertainty in the forcing data, and it would be good to get some information on perhaps that we understand the reasons for the uncertainties and also how to deal with that uncertainty, perhaps if you have a solution to that already.
Yeah, so just extending on what Zeb was saying, I mean, some of the things that I've been having conversations with different groups about is just some of the brain dead zero things that we could do to try and bridge the gap between what is being provided and then what the modelling groups do with it. So, for example, padding years at the beginning and the end. Like if that was systematically done by all modelling groups, then it would be a triviality to add that to next generation data sets, for example. Unit consistency across all the different products. We had issues with that in CMIP6. If there is a standard nomenclature or kind of convention that everyone or the modelling groups are actually building around, then making sure that we impose that on what is coming in. And so some of those really kind of simple little things that actually tries to reduce the number of 15 steps the modelling group takes with any one data set down to 5 would be helpful, or even bring it right down to kind of, you could actually you could copy latest data sets down and use those things natively, which is hopefully, trying to just reduce the steps as much as we can. I think these things are very much probably lending themselves more to the operational part of this workshop rather than the try and get CMIP7 rolling at the moment. But it would be really useful to try and understand from the modelling group point of view how we can try and bridge the gap between what is being produced and then what is being used. And so as much as we could also with data providers to document the data sets, if modelling groups can work the other way and try and figure out what steps you actually go to in order to use them, that would be really helpful. And if there was some simple things that everyone is doing, then we just can bridge the gap between one side to another.
Yeah, good morning, everyone. I just wondered, perhaps we have to do, or perhaps you have to, we have to do more advertising to try and get a diverse set of kind of modeling groups experimenting with the data sets you've got currently. I mean, just because if you're just getting input coming from kind of GFDL, that doesn't seem to be quite what we want. Yes,
Absolutely.
Yeah.
Yes.
So I just wonder if it's worth trying to advertise a bit to say, look, we have got the data set and we do really want you to go and experiment with it, please.
Right. So within the task team, there are at least 4 or 5 modeling groups represented. So, and they have access to the data. So, they're also speeding up to testing the data sets. Additionally, so the data set is already shared on ESGF. And this afternoon, we have a drop-in session to widely announce the availability for the different modeling centers, users, to start looking at the data and and telling us what needs to be done. So yeah, Paul, did you want to add something?
I couldn't agree with you more. I think, I mean, at the moment, we're kind of lucky that we got better organised than we did in CMIP6, which means we do have a small window of opportunity to try and find problems, of which quite a number have been highlighted already, and try and fix them as quick as we can. Because there is going to be a huge amount of, computational time that's expended to try and, make the best simulations possible and the best data sets that we can grab to actually get, drive those simulations would be a good idea. I mean, a key point would be because we have these data sets published in SGF, they are being replicated around the globe pretty quickly, which hopefully then also aids modelling groups in picking things up and running with them. We're trying to do as best a job communicating the updates, etc. And, like the better that we can broadcast that information and inform modelling groups and try and get them engaged in the discussion of evaluating data sets, etc., the better off we are. So if you can help.
Yeah, I'm really sorry. So I'm not being critical properly. Right, I spent my mind to, no, don't worry, Carlo, it's not. Well, yeah, I do think that is something that we can do collectively to, that's some of the I will try and go to in my conversation to try and get everyone to kind of take it up and things and do it. Cheers, Paul.
Well, one of the other things I'd say too, and like this is kind of commented yesterday, and we'll try and continue to make this point. In CMIP6, what happened was there was a lot of emails flying around between modelling groups, and that was not a great way of exposing problems or whatever else and letting modelling groups know that there's a problem with this data set that we've discovered, please stop, wait and, wait for a fix. So what we're trying to do this time around is try and expose a lot of those conversations through the GitHub discussions as Vishali was pointing to, which means that if anyone wants to watch that, they can. And it's not exclusive to a CMIP modelling group. You could be anyone that wants to look at that as well. So trying to use forums, etc., that actually enable anyone and everyone to contribute if they want to is helpful. If there's better ways of doing that, if we can, broaden even more the interactions, then I'd welcome it. Although we've only got very limited resources from the forcing dataset provider, etc., to try and actually kind of address some of the issues as well. So we'll do the best job we can, but the more engagement we have, better off we are, I think.
So there was a question online. Piers, do you have some specific suggestion for the IPO on this? Something they're not doing already that you might?
Well, I was just giving it as an action item to myself personally, to just to get out and tell people about it in my conversations. So I mean, because I think all of us together are advocates for this sort of work. So I just think we need to kind of tell others and just become a little bit more evangelical about it, really.
Absolutely, yes. Yes, we're on board for that. Claire.
Yeah, I'm Australia today. So I think this is not the first time that comms has come up, and I think it's a really key point. So I did wonder what are the specific easy wins that we can do right now. I think the GitHub forum came up yesterday and is a really good way of having that dialogue. Something else that has occurred to me though is that there have been some very informationful and useful plots that have been shown by the data providers today, and all of this information will be online, but it can be quite difficult to sort through. Do we have one central landing page? Can we use the CMIP Forcings webpage just as a central landing page to say, look, here are what we think, so that it's easy to find that GFDL fire plot and the noise characteristics? That's really kind of, it tells you a lot about the data very, very quickly. Can we put that somewhere easy and direct the modeling centers, this is your landing page, here are all your links to data sets, and just make the most of the resources we have already and make it easy to find those?
Totally agree. And I think that is part of the documentation discussion that we are now having with our data providers, because we didn't want to detract them or distract them from getting the data out first. So now that the data is coming out, the next step is to put together that documentation as well as initial evaluation out there and share in a way that is easily accessible and understandable. So yeah, thank you. I guess. All right. So I guess we should move on. Great. Thank you. Thank you for the discussion. This is very helpful. All right. Let's get this in. All right. So with this, the slides that I'm presenting here, just to provide a summary of the DECK experimental protocol in CMIP6 as a way to remind us what this experimental protocol was, and then think about how this should change or stay the same for CMIP7. Okay, so the DECK experiment in CMIP6 were the four experiments listed here: AMIP, short AMIP, pre-industrial control, both for concentration-driven as well as for emissions-driven, a 1% per year increase in CO2, and abrupt CO2, and then plus historical. Historical was not part of the DECK, which now we've changed this to have for CMIP7 include the historical with all these other experiments, plus added 3 additional experiments to better quantify the radiative forcings, the anthropogenic radiative forcings. So in each of these, especially the experiments that use pre-industrial control or CO2 changes, in each of these, plus in the scenarios, we had to decide or had a protocol for specifying natural forcings, which would be solar and volcanic aerosols. And so what were they? So for natural, for solar, pi control used fixed mean over 2 solar cycles, averaging from 1st January to from 1st January 1850 to 28 January 1873, solar forcing. And then in the scenarios, we had solar projections based on the most likely evolution of solar activity from 2015 to 2300. So this is the data set that was used in CMIP6. And then for volcanic, we had averaged 1850 to 2014 volcanic forcing. So average over the historical time period that was used in the pi control, as well as in the scenarios. The right at the end of the historical of 2014, the beginning from 2015, the forcing was ramped up to PI levels until 2015, and after that it stayed constant. So this was what we did for CMIP6. Ooh, there is a slide missing. Sorry, let me just see if it got moved. Nope. All right, I will wing it. So the motivation for this experimental protocol was driven by 2 reasons. First, the mismatch or the inconsistency between when we start with the pre-industrial forcings and the historical ramp up, or the right at the 1850. And second was the consideration for sea level rise and the ocean heat content. Before 1850, in the pre-industrial control, it takes a while for the models to equilibrate to any volcanic forcing right at in the pre-industrial control. especially its ocean heat content, and that has impact on sea level rise. So there were a number of studies led by Jonathan Gregory, who pointed out that there was a need to specify pre-industrial control, some pre-industrial control forcing in especially for volcanic forcing in 1850, and then ramp up to the historical. So this was mostly focusing on sea level rise, but then more recently, Pfeiffer et al. Used CAN-ESM to show the same thing for using volcanic aerosol protocol on GSAT simulations. So in CMIP5, there were no volcanic forcing specified in pre-industrial control. We changed that in CMIP6. And so here on the plot on the right, on the left shows two simulations, blue with CAN-ESM without background aerosol pi control. And then the black is the CAN-ESM with background aerosol and pi control with CMIP5 forcings. And so the simulation without pi volcanic aerosols warms less over the historical period. And that, of course, has implications on our estimate of the change in the pre-industrial to present day global surface air temperature. And similarly, in the future scenarios, in the RCPs, there were no background volcanic aerosols specified. So with their simulations, they indicate that the future scenarios with pi volcanic aerosols are cooler than those without. And so the specification of background volcanic aerosols then has implications for our assessment of both sea level rise as well as for global surface air temperature. So then the question is, well, should this change, or, wow, my slides got eaten up or something. So, right. And then additionally, there have been some more work indicating the uncertain role of both of these volcanic and solar forcings in CMIP6 projections. On the right, there is work done by Mei Chim with Tom Aubrey, suggesting that climate projections very likely likely projections underestimate future volcanic forcings and its climate effects in the projections. And on the right, you have work done by Bern, our data provider for solar forcings, highlighting that only the use of stochastic ensemble forcing scenarios would ensure a realistic quantification of the impact of natural forcing uncertainties. And then, of course, this then ultimately increases the confidence in climate projections. So all of these are up for discussion, and both Tom and Bern will be presenting today to then help us inform the CMIP7 protocol for specifying natural forcings for pi control and scenarios in our DECK simulations. So just highlighting two questions here. And then additionally, for the historical simulations, there has been a significant number of studies highlighting that the model climate response is sensitive to the observed episodicity of biomass burning aerosol emissions. John Fasulo will be talking and highlighting this in much more detail, but what basically this means is that the sudden increase in the biomass burning emissions variability over the satellite period beginning in 1997 to 2014 then acts to weaken the aerosol forcing. So that leads to more warming, and especially over the high latitudes. And then if we temporarily smooth the biomass burning aerosol emissions, and that would then likely overestimate the aerosol forcing. So making it more negative. So then the question is how to deal with this observed natural variability in the biomass burning emissions in our simulations for the historical period. Additionally, the impact of the impact of natural variability in ozone has been highlighted as a problem in the CMIP6 models that use prescribed ozone. So models with prescribed ozone concentrations have this realistic natural simulations or historical simulations of QBO, which is basically an artifact of the prescribed ozone forcing data set that included this realistic simulation of QPO. And so then the implication of this that was highlighted by Butchart in 2023 paper is that the ensembles are not completely independent, and therefore that has implications for the assessment of climate variability. So Michaela is lined up to give a talk and address this issue. So then two questions that maybe we discuss after the presentations is that for the PI control, and then the second one would be that should the interannual variability enforcings that are influenced by natural variability, such as biomass burning emissions and ozone, be smoothed out for historical simulations. So with that, we move to more details from our speakers in this session. So I will stop sharing.
Are we going to do questions based on this session first, or we'll go through all the speakers first?
We'll go through the speakers first, and then we can have a longer discussion.
Okay. So we have 4 speakers on volcanic, solar, biomass, and ozone. I think Thomas, you're up first.
Thank you. While I load the slide, I would just say that just like yesterday, this is the outcome of the full team creating the volcanic forcing data set. But I also want to highlight Mei Chim, who is a PhD student with me, and Anya Schmidt, who contributed a lot to the slides today, as well as Chris Smith. And I will start with this paper by May. It's quite a rich plot, so let me deconstruct it for you. Can you? No, this can't show. Okay. Yeah. So this bar chart here is showing you in climate projection SSP 37.0 the time average effect of volcanic eruptions relative to the contribution of anthropogenic forcing. So on various climate metrics such as global mean surface temperature, ocean heat content, and so on. So you have various color. The yellow bar is the effect in CMIP6, and then the other bars show the result of simulation with UKSM conducted by May, where we implemented stochastic volcanic forcing scenario. So the light blue is the contribution from small magnitude eruption. The dark greenish is a large magnitude eruption, and the sum of these two bars is the median effect we expect in the projection. And then the yellow bar is essentially the 95% confidence interval. And so we have several messages based on this plot. The first one is if you look at the median effect of volcanic forcing in this projection in the future on these various climate metrics, it's 3 to 7%. I think even that is not exactly a small number. And then if you remember that it's in a high sensitivity climate model in a low mitigation scenario, SSP 7.0, essentially volcanic forcing matters for climate projection. It does have a significant effect on all the climate metrics we care about. The other thing is if you look at CMIP6, so the yellow bar, and you compare it to median projection, you can see most of the time, I mean, for all climate metrics, volcanic forcing impact on climate is underestimated in CMIP6. In fact, for most of the bars, it's at the same level or below lower end a lower end limit for volcanic impact on future climate. So there was really a bias in CMIP6. And there are mostly two reasons for that bias, and that would be my main two part of the discussion today. One is related to the effect of large magnitude eruption, so these darker bars. And the reason for that is that the baseline in CMIP6 was 8050 to present for scenario MIP and PyControl, and there are not a lot of large magnitude eruption between 8050 and present day compared to longer term time average volcanic record. And then the second reason is that small, oh yeah, and I would just point out, we do have the same problem in CMIP7 if we pick out the same baseline. And the second problem is that there's a strong small eruption bias pre-satellite era in CMIP6 and also currently in version 0 of the CMIP7 dataset. So essentially that Sion forcing was mostly missing in CMIP6, which explains why the overall volcanic effect on climate was small. So that affects scenario simulation, but also PyControl simulation. So first I will start by discussing the baseline and how choosing the baseline period for PyControl simulation and scenario simulation affect the amount of volcanic forcing we have. So that's the time theory of stratospheric aerosol optical depth, SAOD, as for version 0 of the CMIP7 dataset, and at the top I've included some time average for a 50-year period. And you can see these time averages are highly variable. For example, the early 20th century is quite quiet compared to the early 19th century, where the mean SAOD is 3 times larger. And that's because there are really big eruptions like Tambora, an unknown one in 1909, and a couple more in the late 1930s. And so essentially, I think a good point for discussion today is what baseline period should we pick for PyControl in CMIP7. So I think from Vaishali just reminded us that the spirit of PyControl simulation is that the forcing should be nearly equal to that at the beginning of 8050. So what does that mean for volcanic eruption? I think it's a tricky question. I'm not sure that 8050 to present day is the most relevant period to know what the climate was like in 8050. If we think about how long it takes for climate to adjust to volcanic forcing, it's around 10 to 15 years to return to pre-eruption temperature in terms of global mean surface temperature. If we talk ocean timescale, it's hundreds to thousands of years. So it's really a complicated question. Just as an example, if we picked as a baseline 7050 to 8050, the mean SAOD would be 0.02-ish, and that would be about the same if we take 1800 to 1900. But if we take 1850 to 2023, that would be quite a bit lower. It would be about twice lower. So that baseline choice is really going to affect what we put in PyControl simulation and in scenario simulation. I would just make a note that this is looking at volcanic forcing at centennial timescale. If you look at multi-millennial timescale, this table here shows you for the last 8 or so millennium, the mean SAOD for each millennium, and then the associated mean volcanic cooling. And so you can see that even at multi-millennial timescale, there is a lot of variability. For example, the mean volcanic forcing between the 6th millennium BC and 3rd millennium BC, there's a difference by around a factor of 2. So even if you look at long-term record, the choice of baseline period will have an impact on the ultimate forcing we put in the simulation. And I also want to make the point that whatever we put in PyControl, it's quite unlikely that would correspond to the mean forcing that we put in scenario projection, because the mean forcing we expect is related to the long-term volcanic records and not so much to what it was like in 8050. So of course we want what goes in scenario projection to be consistent with what's in PyControl simulation, but also we should note that what we expect, the mean expectation for the future is not what it was like in 8050. and that's a bit of a problem. And then related to this variability in volcanic eruption, I just want to make one last point. So another paper of May that's currently under review, she used the FAIR climate model to run thousands of projections in the future with different stochastic scenario and contribute and quantify the contribution of different factors to uncertainty in projection. And so that's sort of your standard IPCC plot with scenario uncertainty in this green shade. Model uncertainty is white, internal variability is blue, but we added volcanic uncertainty in orange. And you can see that no matter what time horizon you look like, volcanic uncertainty is actually quite large and always exceeds internal variability uncertainty. And so essentially we have this question for scenario MIP, and I'm not sure if there is anyone from scenario MIP online, but would our computing resource be better spent sampling volcanic forcing uncertainties and even more widely natural forcing uncertainty rather than internal variability? And should we have a bit of a shift in philosophy there? Yeah, and I feel like Bernd from the comment that Vasily just showed maybe wouldn't disagree with that. And obviously we can't have all the climate model running with different stochastic forcing. I think that would cause a big headache for scenario MIP, but maybe at least we could quantify the upper end and lower end level expected in terms of long-term time average volcanic forcing. And so what this plot is showing you is a projection. I think that's SSP2 4.5. Red is with CMIP6 forcing, blue is May stochastic scenario, so it's the median, and then the two dashed line are the 5th and 95th quintile in terms of long-term time average SAOD. And then the blue shading is the actual 95% confidence interval from a stochastic run. But you can see it's not perfect, but if we were running free forcing, natural forcing scenario for the future, essentially that dashed line, the blue line and the dotted line, at least we would sample some of that uncertainty a bit better. And we could imagine construct similar forcing scenario for other natural forcing and maybe have free set of natural forcing for scenario MIP. So that's maybe what it could look like. It's just one suggestion, but essentially we think it's an important problem. Okay, so I'm done with large magnitude eruption. I don't know how I'm doing time-wise, but hopefully you can cut me if I'm too long. So I will go back now to small magnitude eruption, where the problem is not so much that they are very variable in time, but it's more the bias that we have before the satellite era. Just as a reminder, these are all the eruption in the current version of the CMIP7 dataset, and so we have all the small eruptions from 1979 onwards and almost none before. And so we have some, we think we have a fix for that, but essentially I want to discuss it with you today. So this plot here shows you the decadal emission from small magnitude eruptions, less than 3 teragram of SO2. So in blue is CMIP7 version 0. So it's what I just showed you. So you can see this really high bar for the satellite era. And then if you look at the blue bars before the satellite era, they tend to be 0, absolutely no emission, or they tend to be much smaller than what we see during the satellite era. And so essentially we have two data sets we could add to CMIP7 0. The first one is an ice core record from Greenland. It's high resolution, so it picks more small eruption, but it's Greenland only. So we have no idea what went to Antarctica in terms of volcanic aerosols. So it's really hard to identify southern hemisphere eruption. It's really hard to identify which eruption are tropical versus high latitude. So it's not an ideal data set, but you can see just using that data set increase emissions. So it's the orange bar, at least for the 18th and 19th century. And then the second option we can is start using the geological record. And so that's when we add the geological record, it's these yellow bars. You can see it increases emissions further. The problem is that the geological record doesn't say anything about how much sulfur was injected into the stratosphere. And so it's essentially very crude assumption to go from essentially the ash deposit to an SO2 mass. Nonetheless, if you look at the mean emission over the pre-satellite era period, this is CMIP7 V0, 0.16 teragram SO2 per year on average for small eruption. If we had the green line high resolution record, that doubles. And then if we had the geological records, it almost nearly double again. And for reference, that's the emission average over the satellite era. So it's sort of what we think would be a good average. And we get quite close to that when we had these two data sets. Also for reference, this is the flux of SO2 from large magnitude eruption. So it's 1.2 teragram SO2 per year. So you can see that what we miss in CMIP7, roughly 0.4 if you look at the difference, or 0.5 if you look at the difference between CMIP7 V0 and the satellite era for small eruption, it is a big fraction of what the big badass eruption are injected. So it is a big, relatively important missing forcing. So quick look at what happened to SAOD when we had this new data set in CMIP7 V0. So on this plot is global mean SAOD. Red is CMIP6. The black continuous line is CMIP7 V0, and then dashed line and dotted line is when we had this data set. If you look at it quickly, you won't see much difference. You have to look at specific time period to see that the dashed and dotted line increase volcanic forcing a bit. And if you look at the difference between when we include the new ice core record, which is labeled D4I, and the geological record, GVP, it's even smaller difference. So the geological record is highly uncertain, but also because it only adds small perturbation in SAOD, we think it's fairly low risk to add it, meaning there won't suddenly be a massive eruption that we are actually very uncertain in the historical record. And if you look at time average SAOD when we had these data sets, so in this table, this column is the 8050 to 2014 mean, so CMIP7 V0 plus the Greenland ice core plus the geological record, and then that's CMIP6 for comparison. So currently CMIP6 and CMIP7 V0 are almost the same, but if we had all these new data sets, we increase the global mean SAOD by roughly 30%. We would increase the SAOD by 30% in what would be the CMIP7 fast track version compared to what we have now, and also compared to CMIP6. And then that's the average SAOD over the full 7050 to 2023 time period. So to summarize, if we had this Greenland ice core record and the geological record CMIP7 V0, we think the pro is we have much smaller eruption bias pre-satellite era, and the SAOD accordingly increased by roughly 20 to 30%. The con are that we have a risk to introduce false positive in eruption because these assets are very uncertain, but essentially we think it's not a greater risk than having false negative currently, meaning lots of missing eruption. And they're also very small magnitude eruptions, so there's a negligible risk of suddenly introducing big forcings that are not real. I think I'm doing very poorly time-wise, so point for discussion, what's the best period to define climatology for pi control? You've just heard what we plan to do for the historical data set. So we lean towards adding this high uncertainty Greenland ice core and the geological record. But if you have any thought on that, we would really welcome it. And just a heads up that if we do that, there will be a change by roughly 20 to 30% in the time average forcing between the version currently online on the SGF and what we would output for fast track. And then scenario MIP, we really think natural forcing matter. Yeah, and with it's worth a discussion, was it a discussion for before CMIP7 or some research to do during CMIP7 with the aim to change things for CMIP8. Yeah, I will stop here. Thanks for your patience.
Cool, thank you. I think a couple of quick questions now, just while it's fresh in people's minds. So, what's the question online?
The proxy records for volcanic eruptions before 1750.
Right. So there's a question online which asks what the proxy records say for volcanic eruptions before 1750.
100 to 200 years before.
So yeah, somehow my WebEx disappeared, but by proxy record, I guess whoever asked the question means 3 rings, or is that
the ice core or the ice core? What, just for the immediate couple hundred years before 1750? Do we have information that help us, nail down what we should be thinking about there?
Yeah, sorry. So maybe that wasn't really clear, but before the satellite era, our data set is currently almost entirely based on ice core. And one of the 2 data sets we propose to add is also ice core based. The only difference is that currently we only use bipolar ice core, meaning where we have synchronized ice core in Antarctica and Greenland, because that tells us about whether it was likely a southern hemisphere tropical or northern hemisphere eruption. The new ice core that I said we want to add is Greenland only, so it has that limitation. But the pro is that it's high resolutions.
Right. So my question was this question of what we should do for pi control before 1850. So do we have any information just for 1550 to 1750 from the ice cores to get a sense of were the larger eruptions less or more frequent there in terms of the spin up and pi control average?
Yes, so we have very good, for large magnitude eruption, we have very good ice core record going all the way back now to 11,000 years ago. So we do have that information. So the only question is what period do you want to pick as a baseline for pi control and what makes the most sense? I feel it's a tricky question, and essentially I was very keen to hear everybody's thoughts today.
Yes, I was wondering if we would want to use like the 200 or maybe even 300 for sea level rise average before 1850, not just the 100 years.
Yes. One thing that would make me a bit nervous is that if we try to fix the small eruption bias, the geological record is okay. It's quite good up to 8050, okay up to 7050, and before that is really quite poor. But we could use the ice core record. Yeah, if we decide that, say, 1550 to 8050 is the good baseline, we could definitely do that.
Thanks.
Yeah, so John, are you online? John Dunn? There are a couple of questions in the chat. Hmm?
So there was a question earlier on. There was a question earlier on from John. Is there a need to set a background volcanic emissions from post-satellite period for the pre-satellite period? Did you want to come on that?
Yeah, so essentially, if we implement this fix, we think we remove most of that need. Not entirely, because you can see the flux from small eruption in our hopefully new data set. That's what we do, is still smaller than satellite era, but it's quite close. The reason we're not too keen on adding a background is because we would like our data set to be consistent for emission and aerosol depth. And if we decide to add a background, then we have to tell models learning from emission, essentially inject some continuous SO2 flux in the stratosphere at some specified rate, some specified latitude. And I think that opens a bit of a can of worm. Models learning from emission for stratospheric volcanic aerosol should be a bit niche, but I think they are the future. And so we're quite keen to keep these two data sets consistent. I think as long as we document these biases properly, and as long as we try to do better than CMIP6, yeah, I would hope that's a good step.
Do you want to ask that one? And then I'll come in on the scenario thing.
Okay. Question from Julie. Julie, did you want to come in?
Yeah, sure. So this question may seem very general for all forcings, but I raise it here because I know nothing about volcanic eruptions. We have internal experts like Myriam Caudry who know all of it for us. But what I know is how to warm up my model if it's too cold. And I also know how to cool it down if it's too warm. So my question was rather for the other modeling groups, how do you actually arbitrate when you add up a new version of, let's say, the one that we're proposed here, and you end up having a cooler version of your model? Then you also know how to warm it up. How do we arbitrate when we do this or when we don't? And when do we communicate among each other about what we need to be doing? Because of course there are adjustments and uncertainties are very numerous in all our models. So my point is precisely, do we do our internal kitchen stuff and then when we are happy with the result, then we share? Or do we actually share the tricks that we have to do to make it work?
You want to come in on that?
Thank you. Actually links quite nicely with the previous question, because I do see this issue of discontinuity around present to be common to many forcing. So I understand how you're tackling in this context, but I was wondering whether there is scope in looking across forcing to have a common approach for all forcing on how to deal with this discontinuity, and especially discontinuity on the spectrum. So I mean, one of the points you mentioned is this small eruption, and I think it's the same for the solar forcing somehow. So I was wondering whether there is scope in looking across. Thank you.
I was going to briefly comment on your scenario question. I think you make a good case that you can consider the stochastic volcanoes to be essentially part of our internally generated uncertainty for the future, and that's the way we should treat it. I think my main worry would be that if we had n different volcanic stochastic forcing data sets for the future, and then a large fraction of model or some fraction of models only ran the first 2 or 3 initial condition ensemble members, then those particular arbitrary stochastic patterns would be highly upweighted in terms of the database. So if it was truly random, I would be less worried about it, but I would actually be more worried about there being specified forcings number 1, 2, 3, 4, 5, you know.
Yeah. So I totally agree with that, and you don't want your projection to all look like there is a massive eruption in 2040 if there isn't, because that would cause a bit of communication problem. So what we actually propose, because we know it's unrealistic for scenario MIP, is not to do stochastic volcanic forcing, but to have maybe all modeling group run at least 3 scenario projection, and at least one must be a lower end natural forcing, but still constant, and at least one must be an upper end natural forcing, still constant, and then as many member as you want on the median estimate for future natural forcing. And the way this upper end and lower end natural forcing could be derived for volcanoes, or also could come from like stochastic approach, or that doesn't really matter, but keep it constant because it's challenging for scenario MIP to do something else, but at least have one lower end member and one upper end member. Yeah.
Did the results you showed not sort of imply that that the mapping between forcing and temperature response is conditioned on the statistical distribution of the volcanoes, though? In the future simulations where you had the same forcing level, you had more cooling, if I remember correctly, in the one with stochastic volcanoes. Or did I misread that? Like implying if you're not sampling this stochastic distributional aspect, then you're missing something.
Do you mean on this plot, comparing the yellow bar to the other bars? Yeah, no, so the difference in mean climate effect between the top bars, the stochastic and the yellow bar, is not because one is stochastic and the other is not. It's because the CMIP6 forcing is lower. In terms of mean forcing, because there are not a lot of big eruption since 1850, and because there's a big bias in small magnitude eruption. options.
Does Gavin, do you have a question?
Hi, thanks. So a couple of questions. I mean, one, lots of people are doing kind of last millennium simulations as well as historical simulations, and I think we should be aiming to have a consistency between the last millennium simulations and the historical simulations, which should suggest that the pre-industrial control spin-up should use the average of, you know, the previous 100 years or so of both solar estimates and volcanic estimates. So I don't think that that's too problematic. For the scenarios going forward, though, there's no way that we can do a full suite of all the possible volcanic simulations within the ESMs themselves. But this is perhaps a great example of where more sophisticated emulators could be brought to bear, where you could in fact run as many different volcanic scenarios as you wanted, as long you know, and then kind of use that as information to when you're making your assessed predictions, which are not using the raw climate model data. So that can be kind of put on kind of post hoc, if you like, in terms of what impact that might be. And it seems that we have to do something along those lines, because we're never really going to be able to do as many volcanic simulations with the full ESM as we would like. Thanks.
I think that's a good point. I feel like we might need to push on and do one more before the break, and then we'll do the last two after the break. So we've got a presentation on solar now from Bernd.
Yes. So let me just try to share. Okay, do you see my screen?
Yes.
Okay, so this is about the solar forcing, and I'm going to give a little bit more details than yesterday about the changes introduced in the current version for CMIP7 compared to CMIP6, and also some details on the plans regarding scenario solar forcing. And let me start, as yesterday, with acknowledging the large group of people who contributed to the generation of the solar forcing. And I wanted to start with just the schematics, how solar forcing is implemented in climate models, just to give the context of the different data sets. So the solar forcing consists of two parts: the radiative part, the TSI, SSI, and the particle forcing part, which is generally provided in terms of ionization rates and only affect chemistry. So ideally for a fully coupled interactive chemistry high-top model, one would introduce these ionization rates to compute the chemical changes introduced by energetic particles in different height regimes of the atmosphere, and introduce, of course, also the radiative changes, which affects the chemistry. Then there's the class of models which do not extend up to the lower thermosphere, but have interactive chemistry included. For these models, the production of nitric oxide, which is then destroying ozone later on in polar winters in the stratosphere, has to be prescribed in terms of an upper boundary condition. But what is most typical for models in the framework of CMIP is, of course, a model which does not extend up to the mesosphere, or at least not into the lower thermosphere, and has no interactive chemistry. And there, the solar forcing is, at least for the particle, energetic particle part, is entirely included in the ozone forcing, and this highlights the need to have a very consistent and complete description of solar forcing in the model runs, which will produce the ozone forcing. So I think this background is important. And so I would like to start with the changes, or well, let's say with the history of changes in the radiative forcing, putting the CMIP7 data set in context with previous CMIP releases. So regarding the TSI reference values, there have been quite important changes. For CMIP5, the TSI was about 5 watts per square meters higher than for CMIP6. And now in CMIP7, we will have again a slight increase, so slightly back to CMIP5, but it's only about 0.6 watts per square meters. Then regarding, well, let me first start with a quiet sun spectrum. So this is a solar reference spectrum, which defines the spectral distribution of the energy. Regarding the changes to CMIP6, we now use the version 2 of the HSRS, high solar spectrum, by Coddington et al., which has some important changes, which I will discuss a little bit more in detail in the next slides. Then regarding the source for SSI variability, while for CMIP6 we used an average of 2 models, the NIL SSI2 model and the satire model. For CMIP7, we have decided not to go this way and use one of the models, which is the successor model of NIL SSI, the NNL1 model as a reference, and the satire model as an alternative data set for sensitivity studies. I think this is the most important part to mention here. Just going into more detail in the new solar reference spectrum. Well, the reason why we adopted this new solar reference spectrum is first because it is now recommended the new solar irradiance reference spectrum standard by the CEO's working group on calibration and validation. And this is largely motivated by the high accuracy of this data set. There is an important change with respect to the previous versions, what has been implemented in CMIP6. So this spectrum has enhanced energy contribution in the UV of 1 to 5%, and the decreased contribution with respect to CMIP6 in the visible. And this has direct implications on the climate response, because the sea ice albedo is higher in the visible, lower in the near infrared. So this is has a direct impact, particularly for the polar region surface climate, and need to be considered in climate modeling tuning activities. So the other change is the change in the total solar irradiance reference value. And immediate question is, how final is this new TSI reference? And well, history has shown here in the example of the determination of the electron charge that the back and forth is quite typical and needs to be this way. And for the total solar irradiance, the question is whether we are in the range where the value is getting stable, or if we are in the range where there are still large oscillations. So it is expected that, well, first for CMIP7, regarding the preliminary version, which is the current version 4.4, we don't expect any further change of this reference. There might be a change in CMIP8, who never knows, but we expect that future changes will be of considerably larger, smaller amplitudes than changes with respect to previous versions. So the third question which might arise is why we don't merge again the NNL1 and model and the satire model. So the reason is that while for the recent satellite era period where very good observations are available, the agreement on short-term variability between both models is very good, which would allow for merging of both models. This is not the case for the early period of the CMIP7 or the CMIP period, where we rely entirely on proxies. So there is an out-of-phase short-term variability in the two models, which would significantly complicate the merging because it would lead to a dampening of the variability magnitude and unrealistic variability patterns. So this is the main reason why we decided to decide for one model, but I would like to highlight that the decision on which model to take is purely for practical reasons and not motivated by quality of the models or scientific reasons. So just to show the difference between these two models, so the plot shows in red the satire data set and in black the CMIP7 reference. So in general, the models agree very well on the annual scales. So there are slight differences which are generally smaller than 0.2 watts per square meter. But this is a big improvement regarding the consistency of the models with respect to earlier times. And regarding the SSI, so what I'm showing here is the difference between solar max and solar min. There's a slightly larger UV variability in the satire model compared to CMIP7 reference. But this is, well, I would say, mostly within the uncertainty of the data sets. I showed this plot, this slide already yesterday, so this is a kind of nutshell comparison of CMIP7 versus CMIP6. So just to remind, the slightly larger reference value of 0.6 watts per square meter, slightly smaller secular trend, enhanced irradiance in the UV opposed to the NER, where it is reduced, with likely important implications for related to sea ice albedo, which need to be taken into account, and then a slightly smaller decadal variability in the UV regarding the solar max versus solar min changes. Okay, so coming to the energetic particle forcing part, and it is clear that this is not that relevant for direct implementation in CMIP7 models, but it is relevant for the generation of the ozone data set. And I just want to remind with the plot here on the right from the WNO UNEP ozone assessment 2018, where it is shown that the neglection of energetic particle forcing on ozone due to the impact of descending nitric oxide contributions from the thermosphere can lead to differences, biases in the order of up to 30% in polar winter ozone and in biases in the ozone column of up to or close to 10%. So the changes are, I just quickly go through that. There will be some improvements regarding the representation of the energetic electron precipitation. and some other small improvements which will not drastically change the impact on ozone. So the major improvement relies on the side of the energetic electron precipitation. So this slide is about the future solar activity scenarios, and that has already been brought up in previous presentations, a little bit the question about how to deal with natural variability in scenarios. So just to go back in history, in CMIP7 a stationary sun scenario was proposed, basically consisting in a repetition of solar cycle 23, which did not include existing long-term variability of the sun, mostly related to Gleichspec type cycles, which have been included in CMIP6. So what has been done was to look at the past solar activity evolution from cosmogenic isotopes and to look at plausible future evolutions based on this past evolution using different methods, so analog forecast, autoregressive methods, or harmonic forecast, and we came up for CMIP6 with two scenarios, one reference scenario and an extreme Dalton type minimum scenario. So for the problem with such a scenario is, of course, that it is only one realization, and there are some stochastic elements in the solar forcing, as for example strong solar proton events, which have a timing which might interfere, for example, with the ozone recovery. So strong solar proton events in the around 2050 could reduce to ozone reduction in the stratosphere, which might then introduce an earlier or a later recovery. So these things need to be considered, and we have been thinking about what to do in CMIP7. As mentioned earlier, ideally one would come up with an ensemble of solar activity evolutions and use such an ensemble forcing, which of course is not very realistic from the computational cost point of view. Nevertheless, we think that it's worth to generate such ensemble forcing scenarios just because it might be possible to use such scenarios by means of detection attribution methods in order to look at natural forcing uncertainty without the need of running full ensembles through climate models. So the idea would be, that is our suggestion, to provide one reference scenario, or as suggested earlier by Thomas, maybe one max and one min in addition, but to provide also an ensemble which could then be used for an assessment of the uncertainty in terms of detection attribution. So I think I had this slide already yesterday, so this is about status and timeline. So we have the version 4.4 available on input for MIPS. So regarding this version, the radiative forcing is deemed to be stable. So we do not expect any further changes, while for the particle forcings, there are current ongoing refinements, which we hope to solve within the next weeks. And the final historical data set will be ready until January 2025, and we will work on the future solar forcing, including inputs of this discussion here until end of next year. So thank you very much.
So I don't know what we want to do for the lunch, the coffee break now. Whether we want to pause before questions. Maybe do you know, no more than 5 minutes of questions now, and then we'll go for coffee.
Were there any questions?
So.
Thanks, Bernd. Also, massive thanks from, I think, Paul and I for all your efforts over the last months getting data out and retracting versions and stuff. You guys have been the absolute guinea pigs for us, and it's made a big difference. And I think for all the other forcing providers, they can thank you as well, because you've dealt with the bugs that they won't have to deal with, which is always nice. I think on the natural future stochastic stuff, Chris and I should definitely get our systems running, because we always have an excuse to crunch things with our models. And
literally just wrote that in the doc.
Yeah, good. And that's I think we're probably the easy way to do this without blowing your computing resources, but you get a pretty good answer pretty quickly. So both for volcanic and solar, we should do this and see what it looks like, and then we can follow Thomas's case and make the case that internal variability is a waste of time and everyone should just do this instead with the numbers behind it. The real question I had was, Bernd, for the future scenarios, yesterday you mentioned end of 2025. Could you get something on the fast track timeline? So something for future solar forcing by, I don't know, let's say June 2025 instead, being very ambitious, and see what you think.
Well, I see some reasonable chance to do that until mid next year. It will be, well, time for doing tests on this data set will then be pretty limited, but from the methodological point of view, I would think that it should be ready until mid 25.
More questions? If not, I have one. It looked on your plot of the revised TSI CMIP6 and CMIP7, like pre-1900, there was both more variability and a slightly different mean in the 1850 to 1900 average. Do you have any feeling on how much that would contribute to a diagnosed warming between 1850 and an 1850 to 1900 average and present day? It looks like it could be on the verge of being significant.
I'm just trying to get up. You're referring to this slide, aren't you?
Yeah. So yeah, the difference between the red and the black line pre-1900.
Yeah, exactly. Okay, so the reason for the divergence towards the last 50 years of the period is mostly related to the uncertainty of the sunspot number records, which have been used in CMIP6. So there has been recently a revision of the sunspot number, resulting in sunspot number version 2, which is also some further discussions going on whether for long-term reconstruction this is the right thing to use in terms of consistency with cosmogenic isotope records. So what is now implemented in CMIP7 is a compromise, which is supported by most of the specialists, which is slightly lower than sunspot number version 2, but well in line with the cosmogenic isotope records. And the rationale for doing that is twofold. One is in order to facilitate a connection to the PMIP time period and the PMIP forcing, which has also been mentioned earlier today. And then that there's general consensus that the sunspot group number, which has been used in CMIP6, is on the low-hand side. Of course, there's a large error bar on this TSI in this early period anyway.
Yeah, thanks. One more, then we'll go Philip.
Yeah, I sort of did find this diagram very interesting. And it does seem to me there's a lot more kind of certainty that the TSI hasn't really changed. And we have a lot more certainty than we did having it before. But perhaps you could just be explicit about kind of where you do think the big uncertainty is currently.
Oh, that's a good question. We have a lot of ongoing discussions how to quantify uncertainties for the solar forcing. Our aim is to include uncertainties in the data set. It's not fully clear if we will manage this for the final data version or if this has to be delivered later on. The problem is that there's several domains where uncertainty act on at different scales. So SSI uncertainty is something different than TSI uncertainties. On the other hand, SSI has to sum up to TSI, so it's not straightforward how to report such uncertainties, and even more important, how to include them in, or how to consider them in our climate simulations. If we talk about the reduction of uncertainties with respect to CMIP6, I would say that regarding SSI, there is a reduction of uncertainty related to the use of the new reference spectrum, which is based on instruments which higher accuracy than previous reference spectrums were. Similar holds for TSI. So regarding the absolute scale, the new instrumentation, which is active since about 10 to 7 years, has allowed to reduce the uncertainty. This hopefully will be reflected in the uncertainty estimates we are planning to provide.
Okay, I suggest we break for coffee now. There's a big question from Carlo in the chat, but I think we should leave it till afterwards because it's a big one. Yeah.
Okay, so if everyone can aim to be back maybe 11:05. Okay.
Is Michaela online?
No.
Yeah, I don't.
Allergy tablets.
Then we just go with. And you got your mic.
Sorry.
Thanks for having me, and my apologies for not being able to attend in person. This is work that we've been doing over the past several years at NCAR, and my main collaborators on the work are Nan Rosenblum and Rebecca Buchholz. And the work was really kicked off by our experience with the CMIP6 biomass emissions during production of the CSM2 large ensemble. My goal here is to cover a few papers we've done recently, starting with this paper we did on the climate responses in CSM2 to the CMIP6 biomass emissions, and that was in GRL in 2022. But then I'll go on to discuss some other contexts in which biomass emissions are important, and that includes the responses to the 2019-2020 Australian wildfires, and some more idealized experiments that look at biomass emissions as a coupled component of ENSO. To finish it up, I'll try to touch on some coupled climate feedback experiments where we're actually getting the biomass emissions from CLM directly. So the wildfires are directly coupled to the climate system in these simulations. So the first paper I mentioned was this paper looking at the climate response to CMIP6 forcings in CSM2. What we found during our initial simulations was that we were getting substantially more warming late in the historical era in CSM2 when we use the CMIP6 emissions. And that's shown on this figure on the right, where you can see the global temperature in the red line. And through the end of the historical era, we actually got quite a bit more global warming, but particularly strong warming from 30 to 90 north. And that's in the top right. And that's compared to CSM1 in the blue. And what struck us as odd is that the transient climate response in CSM2 is actually less than in CSM1. And so why do we see this greater warming? And so when we looked at the biomass emissions in CMIP6 on the left, what we found is this discontinuity in the variability between the satellite era and the rest of the historical era. And the question this raised is whether that variability could actually be driving warming. On the right-hand side, you see a number of other effects that are associated with this increased variability in the emissions, and you see a reduction of albedo overall, more shortwave absorbed by the system, and that's really what is driving the warming in these simulations. So in these experiments, it's the monthly mean emissions that are identical and only the variability that has changed. And this raises a question as to why variability in the emissions would actually drive warming. And it turns out that there are actually two nonlinear relationships that are important. The first is the relationship between CCN and cloud droplet number. So that's shown in the bottom left. And the second is the relationship between cloud droplet number and shortwave radiation. And that's shown in the top right of the left-hand panel. Both of these nonlinearities mean that when one includes variability and you get these really high years of emissions, the system starts to saturate and you don't get a very strong radiative response to the higher emissions. But at the same time, you get more of a response consistently to the low emissions. And in the net, that drives a warming. The biomass emissions, again, the climatologies are identical. On the right-hand side, you see the patterns of warming that this drives. So temperature on the top left, predominantly at high latitudes, and a cloud droplet number on the top right, the low cloud amount on the bottom left, and the radiation on the bottom right. So we also see similar responses in other models. On the left, I show the warming pattern in UK ESM based on an ensemble of 5 members, so it's a bit noisy. And on the right, I show the warming response in E3SM2 from a paper we did earlier this year based on an ensemble of 21 members. And what we see is that we have this general similar pattern of warming, and there seem to be similar mechanisms. This, again, is a cloud effect, cloud aerosol interaction effect, that reduces the albedo of clouds and warms the system. The strength of the interaction in different models is certainly different, and there's a lot to be understood in terms of what the right answer should be. There are many links in the chains that connect aerosols to clouds and radiation, and this is not something that models do particularly well, in part because the vertical distribution of clouds and aerosols is actually quite important. So whether these things are co-located in the vertical or whether they are separate really impacts how strong the cloud responses would be. And so I'd say this is very much a work in progress. I'd note as well that we've done similar experiments using the GISS model, the GISS E2 model, and found no detectable response. We think that's because of the relative simplicity of the aerosol schemes in the model, and they changed a lot into version E3, and we are in the process of doing some experiments in E3 to examine what that effect might be in the newer model. So these effects actually aren't all that new and were published on in 2015 in this paper by Clark et al. And what they looked at were the influences of episodicity in fires in CAM5. And so they're basically looking at how you represent fire and at what timescales you represent fires. And what they find is that as you get to these higher frequencies of fire, you actually can drive warming by this episodicity of the fires themselves. And so this isn't all that new, and it probably should have been something we anticipated in CMIP6. But it's interesting to note that this was published on back in 2015. We've also found evidence that fires can be important for seasonal prediction. This is from a paper published last year in Science Advances, where we use our initialized prediction system called CSM2 SMILE to identify a La Nina-like response to the Australian fires in 2019 and 2020, and that this response lasts for several years. On the top right, you can see the evolution of Nina 3.4 SST anomalies with the Australian fires in the red line versus the climatological fires in the black line. Below that are the spatial distributions of anomalies in the lead up to year 1 and year 2 La Nina events. So both years show a pretty clear La Nina signal. Now, we only ran these ensembles for 4 years, and so we only caught these 2 years of La Nina because we didn't expect such a prolonged response to the fires, actually. So we couldn't say whether there was a year 3 La Nina event, which is an interesting question because that's what we saw in nature. But we're still kind of looking into these long-term responses to the fires. We did delve into the mechanisms that drove the La Nina events and connected the fires to ENSO. And we found that the aerosol cloud interactions were actually a key part of this as well. The top panel shows the reduction in solar flux over the globe due to the fires. And you can see it's a particularly strong reduction across the southern hemisphere, and particularly in the southeastern and South Pacific Ocean, just after the peak of the fires. This is January 2020. So you're looking at a reduction of about 20 watts per meter squared in solar radiation. And of course, this drove a cooling of the surface as well. So in the time series below, the red dashed line, you can see the time series of the actual aerosol burdens, the responses of the clouds in the thick black line, and then the cooling of the surface in the dashed line, the dashed blue line. And so you get this increase in cloud albedo, the increase in cloud liquid water path in response to the fires. And that in turn cools and dries the boundary layer. So in the bottom time series, you can see the effects on specific humidity and then also in temperature. And together, those really reduce the moist static energy of the boundary layer. And this is important because this air is actually directly upstream from the deep tropics. And so you get this advection of low moist static energy air into the deep tropics that pushes the ITCC northward. And much in the way of volcanic eruption would influence ENSO. When you displace the ITCC northward, you get a increased probability of a La Nina event afterwards. And we think that this may have happened across recent years in the deep tropics. To address some of the questions surrounding the model dependence of this result, we've reproduced these experiments in E3SM2 SMILE. These plots are from a paper in preparation led by Jerry Meal. The plot on the left shows the surface cooling response to the fires, both in CSM and E3SM. And in the first year, you get this kind of direct response to the fires. So you have brighter clouds, you have reduced solar radiation, and you get a cooling of the surface. But over the next few years, you get these feedbacks in the tropics that relate to La Nina. And we see this in both models. We see it somewhat stronger in CSM than E3SM. And we think this difference in strength may relate to the difference of ENSO-related feedbacks in the model. CSM has this very strong ENSO, a lot of variance in ENSO, whereas E3SM, it's weaker. And associated with that, you get a weaker La Nina-like response. You do get this cooling. Now, with these E3SM simulations, we actually extended them out several years. And so on the right, you see the time series of the cooling, and that goes through the first 3 years, actually. And then it's followed by this very strong warming, which is interesting because that's what we saw with this past strong El Nino event in nature. We don't yet have any appreciation for what the mechanisms might be that connect fires from 2020 to an El Nino event in 2024, but this is something that we're actively exploring. We think there are a few key feedbacks going on, and these are in the Eastern Pacific, where you get this coupling between cold surface and thick clouds, and that feeding back onto the Bjerknes feedback, and that's shown in the top left. And then in the bottom right, we also think there's some feedbacks going on in the Western Pacific that lead to a gill-type response where you have warm SSTs and ocean heat content off the equator, and that drives this convective anomaly out over the maritime continent, which feedbacks onto the Walker circulation and couples to the first set of feedbacks that we described. So that's really key to addressing this question of when the smoke dissipates by March of 2020, how do you get a multi-year response to the fires? And we think that these feedbacks in the tropics are central. You could also ask the question, what is the role of fire just generally in ENSO? We've all learned that the ocean and atmosphere feedback via the Walker cell to create ENSO events, but fire was never actually incorporated in that type of a description of ENSO. And so nonetheless, we know from satellite observations, for example, on the left here, that during El Nino events, you get major emissions of biomass off of Indonesia that affect clouds and precip and diabatic heating in the atmosphere, and has the potential, at least, to feedback onto ENSO itself. And so this year we did a paper that's in press at the Journal of Climate that tries to quantify these effects. And we find that various biases in CSM2 are reduced when we incorporate realistic fire emissions, and that this might be an important part of coupled feedbacks during ENSO. And just lastly, we've begun to perform simulations in CSM2 where fire is actually treated as a coupled component of the climate system. So in these simulations, we're using CLM to provide biomass emissions to the atmosphere directly, and the fires see the fire weather generated by the coupled model. So this is very different than viewing biomass emissions as an external forcing. So it's really coupled with the climate system. And what we find is it's actually an important feedback within the system and affects the evolution of global temperature, both in the historical era and into the future. So we run these for various SSPs, but the appropriate comparison on the left, this is global temperature, is between the CSM2 large ensemble, which is kind of this dark purple line, and the black line during the historical, and the red line out to 2100, which is SSP 370, the same as in the large ensemble. And you can see that there are important differences between the global temperature evolution of the large ensemble and these runs with coupled fire. And so the suggestion here is that fire is an important coupled feedback within the system that's relevant both to the historical era and evaluations with the temperature record, for example, and then also as a coupled feedback into the 21st century, and may impact the effective Earth system sensitivity when you allow fire to feed back onto the system. And so this is very much work in preparation. The simulations I would view as experimental at this point, but this is where we are going. And so finally, just to wrap up, we have several papers that demonstrate the importance of biomass emissions in climate, both in the context of climate projections, but also seasonal climate prediction. When you step back for a second, part of the big picture here is that fire intensity, fire extent, and the fire seasons are all going to grow into the future. And so all the effects of fire in the past are actually going to be amplified under climate change. And so all the things that we think are relevant are going to be increasingly relevant going forward, both in terms of seasonal prediction and also fire as a feedback. And so far, the community has largely failed to account for any of these effects. And so going forward, I think this is going to be a ripe area of research and fairly consequential for understanding the future climate change. And so with that, I'd like to take questions, and thank you for your attention.
Yeah, Michaela's online.
Michaela's online, but John is not online.
John's not online, but
Yeah.
there will be a chance to ask him questions in session 4 later, where there is investment.
Okay. Okay, so maybe we just go straight to Michaela now. Yeah.
Yes, hello everybody, and sorry for not having been here in the morning. Because I haven't been here, I don't know how the discussion evolved, and I might be talking like looking like a fish out of the water. But I'll try. Oops, again, I try to share my slides. Give me a sec. Here, almost there. Can you see my whole screen? Oh, that's the wrong one. Sorry. No good. Trying again. Can you see that one now?
Yes.
Vaishali, have you already started talking about the QBO issue?
So I just introduced the issue in the beginning, but that's about it. So
everybody
take
saw
out.
everybody knows what the QBO is, the quasi-biennial oscillation, and how it looks like in the ozone. There's this figure that Vaishali showed earlier with these downward propagating low ozone values and high ozone values. So we are talking about that, and like picking up on the paper from Neil Butchard that he basically said that this is an erroneous feature in the CMIP7 data set that we provided. And I like to question that, whether that is actually a problem or whether we want to go in this direction or whether we should do something else. I think I want to rather instigate the discussion. I'm not kind of going to tell you the solution to it, but I want to just, because we had this discussion earlier in the forcings task team, that in principle, this issue is there in all the different forcings, and well, not in all of them, but in the internal variables. And John's presentation right now, what I heard of it, seemed to exactly indicate the same. Anything that is an internal variable and internal to the Earth system will have a problem if you are going to prescribe these. But if you have CMIP models that do not have these internal variables, like ozone, a lot of these models do not resolve chemistry, they do not resolve wildfires, then what do? We need to prescribe them somehow. With that, I'd like to just come to an example. So there are always interactions between the internal and external variability. In the case of ozone, it is the dynamics that drives the ozone, but the ozone feedbacks through radiative heating onto the dynamics as well. So you never can disentangle them if you do not go and simulate them together. And you can see that in this example of nudged chemistry climate model simulations, in which we nudge the dynamics to observed meteorology. And if you do that and you include the ODSs, ozone depleting substances, in your simulations, if you have the observations in orange, so this is for the global south, this is for the global north. If you nudge your chemistry climate model simulations, then you can follow in this dark black or dark blue or black line, you can follow the observations extremely well. So, so that is taking out the dynamical variability. You prescribe what the meteorology did, and you take that out. And then you can also rerun that with the prescribed meteorology, and you can see that if you take out the ozone depleting substances effect, then you get the blue line, and you can see that if it wasn't for the ozone depleting substances, you would have actually, after Mount Pinatubo, a huge increase in ozone, giving you an example how the dynamics after a volcanic eruption is reacting to the additional aerosol in the stratosphere, leading to differential radiative heating and leading to that transport anomaly. Having these simulations, you can actually take out the chemical effect, and you subtract the two simulations, and you can identify what you would think is or what we know should be the expected response to a volcanic eruption, that is enhanced ozone depletion. You can see it in the southern hemisphere and the northern hemisphere. But if you look into the orange, the observed time series, you cannot see that in the southern hemisphere. We had an increase. So there's this big question: how do we deal with such a peculiarity of the natural system? Do we want to have this in our simulation, in our ozone forcings, or not? So that is where we get a little bit philosophical, because the answer really depends on the questions that we ask. And one of CMIP's goal is for sure to attribute past climate change. And what is indicating here, what we are very proud of is that we can get all the vehicles, and that we can attribute these vehicles to the natural part, which is in this case here the mostly indicated by the dips that we have through the volcanoes in the global mean temperature. So over the historical past, I would thus argue that we want to be as close as possible to the observations that we had and have. If you go to the future, we want to know what the magnitude of the climate variability is, and here the variability caused by ozone and its feedbacks on temperature should be considered. Obviously, that has is a problem with the QBO. You definitely want to have a QBO in your model. If you don't have it, you miss some of the internal variability of the system. So it is perhaps better to prescribe one than not, because for the models that have one, and that was Butchard's point, and where you put the CMIP6 ozone on top of it, then you get some sort of a synchronization within your model ensemble spread, and that leads to less variability. But that is exactly what actually ozone is doing. We expect that it is sort of putting order into the dynamical system by always kind of having that feedback through the radiation. And this is actually an interesting point, and I do not know why they kind of framed it in such a negative way. Just to kind of have a complaint about Neil Butcher's paper here in front of everybody, because if you would look just at this effect, then it gives us order, it gives us a signal, and it's exactly this signal that we want to get at when we want to look into the past and what happened over the past to explain the past. And that is true also when we think of the QBO disruptions that we have. What kind of impact could that have had on the ozone? We know there was an impact. There are studies about that, but then maybe not so much. What are these impacts on the climate, on the surface climate? We don't really have dug into this in high enough detail, but the stratospheric community is certainly set to look at these issues. Anyway, so back to the question, so I want to have a question to you all. So if you had perfect observations going back to 1900, would you want to use them to create our ozone forcing or not? So can I have a hands up? I'm sure at least the ESA people, they would have their hands up. You are too small, I can't see it, and nobody online has put their hands up yet. Can I ask again? If you had perfect observations, would you want to have them in your forcing? Piers, thank you. At least one person who's paying attention. Anyway, all right. There's some. I think there are some in the thing as well. So here on the is just another figure out of Butchard's paper. Well, no, I should go back to this one here first. Yes, it means that CMIP ensemble simulation from a single model with the prescribed CMIP6 ozone are not entirely independent in terms of their internal variability. That's sure. So if one uses those ensembles for some purposes, one needs to bear that in mind in the analyses. So we cannot answer all the questions that we have with the same model simulations. And if we want to, as Butchard puts it, want to have a measure of the noise, then yes, you prescribe your ozone forcing in a different way. You take out the QBO, which they would take out some part of the signal, but you had your model internal variability, and that would give you some sort of noise. But what do you do with that? That is always a question also of how you interpret it. So I think it's not an obvious solution to take the ozone out. The problem remains that ozone is both a climate forcer and an internal variable. And if you really want to do a proper way, then you have to run an ESM with interactive chemistry. And if you impose a forcing through internal variables, that includes also the emissions from the wildfires, for example, it's always going to be a compromise. And I said that already, we have started to discuss that in the forcings task team. And yeah, I think I'll stop here with that. Maybe that was a bit of a ramble, sorry, but maybe somebody has a question who can clarify.
Okay, thank you very much. Have any questions?
Just a slight comment, really, Michaela, because presumably if we have a data set, including the QBO signal, and someone wants a data set without the QBO signal, it's not too difficult to filter that data set to damp out that QBO signal and give something out of it. So if you prepare the data set with the QBO signal plus some instructions or an additional data set where it's filtered out, that would, might be useful for a variety of studies.
Thanks, Tim. That is a very good point. Yes, you can do that, and we are thinking of actually providing such a little code. But again, like we will have to have a big disclaimer on that one, because it is really difficult to disentangle the full effect of the QBO on the full ozone field, because we just don't have we don't have the observations, also like reaching into the troposphere, of how the effect is really affecting the full ozone distribution. And it had, the QBO is not only an impact in the tropics, but it has also a strong impact in the extratropics. And there will be always some shortcomings in doing so. But yeah, we will definitely propose some MLR effect, or we will provide some MLR code that could hopefully take that out in some way or the other.
I just have a clarification question, Michaela. In your CMIP6 simulations and also for CMIP7, do you create the forcings using nudged simulations or free-running coupled model simulations?
Thank you, Vajali. Also a really good question, and I should have pointed that out. We didn't have nudged. We do not use nudged simulations to produce these ozone forcings. It was in my mind. We were discussing that in the team. In the chemistry, climate modelers tell me that if you do that, then you get inhomogeneity when you go into the future scenarios, because the nudged meteorology will have a different climatology than the model climatology. So we will make some tests whether that will make sense, but this is not the current proposed way forward. What we do, and the QBO itself, you can also just nudge the QBO. That was also not the case in the CMIP6 database. But what we want to do for CMIP7 is to prescribe the QBO winds in the 3 models that we use, to at least have the same wind signal in there. So you can imagine these models, they do all, or 2 of them at least, they do produce a QBO, an internally generated QBO, but the phases of these QBOs are very, very different. So we intend now to nudge it towards the observed one, so that we get the phase and the oscillation in the right place. Yeah.
And what would you do for the future simulations then?
We do just take some mean. We have it. So it's not something that we come up with. It's actually the Chemistry Climate Model Initiative. They use that already for their simulations into the future. And they have this QBO database that goes back to the Berlin winds, observed winds. And they have proposed, or they use a very well-established QBO also into the future that is, if I remember correctly, it's maybe the last 10 years of a climatology of the QBO that they propagate into the future, and also the first 10 years of what we have are propagated into the past.
Got it. Thank you, Michaela.
So any more specific questions on ozone before we sort of open up to a more general discussion? Is now a time to sort of ask about your coordinated strategy then? Yeah.
Sure, I'm happy. I put it in the chat and then it's in the document now. But I guess the question, and we were talking over coffee with some of you, the question is, in my mind, we have seen a similar issue in multiple forcing, and that's to do with the fact that from 79 onward, we have a much more precise and high resolution description of this forcing because of the satellites. So this means that the characteristic of the forcing of the last 40 odd years is different from the characteristic of the forcing in the pre-industrial, and is different from the characteristic of the forcing in the scenarios. And we heard about the volcano just before coffee and the strategy there with the stochastic scenarios. And I was wondering whether there is worth considering a common approach for multiple forcing, where the same strategy to deal with the discontinuity in the two directions, so both in the past and in the future, is taken on board. That was my question.
So I was just going to just point out what happened in CMIP7. We did actually have, with the land use forcing data set, a low and a high scenario for the historical, and that was exactly the kind of thing that we started talking about today, which is, can we cap, the way that forcing has been done, at least in the coordinated way in the past. CMIP6 is the best example of this. Was we had these kind of consensus best estimate available data sets that had no estimate of uncertainty other than the land use data set. And I don't know what strategy a lot of the modelling groups actually used to incorporate that. I think that strategy is probably a really good one to think about. What is the possible worst case scenario with volcanoes, for argument's sake? And then at the moment, I think we've got the most conservative, we've got low effectively. And then doing that systematically would be a really interesting project to actually embark on. In the Google Doc, I was having this conversation with Julie about IPSL strategy is to have a large ensemble. Maybe, I don't know, I'd come up with a number, but maybe 50 ensemble members. Would it be a good idea to try and strategize across, say, those 50 ensemble members to try and sample that forcing uncertainty in addition to other aspects too? Now, that is going to be pretty unique, I think, to modelling groups and what their aspiration is to contribute multiple ensemble members. But it would be great to try and do this systematically if we could across modelling groups, particularly learning by doing with this collaborative environment.
Can I comment on that? I mean, generally, yes to coordinated uncertainty approaches, but I think we need to be really, really clear about what we're talking about. We're not talking only about the spread in uncertainty estimates. We're talking about the characteristics of the variability, which is what John was showing. And stability is yet another question over long time periods. What CMIP has wanted above all from us has been stability over sort of centennial timescales, which is, with the observing system we have, very, very challenging. And there are places like Hadest that have tried to address that. But even then, the most sophisticated uncertainty estimates we have talk about the uncertainty components over the time series and don't quantify the stability or the variability characteristics. And we're only just beginning to explore that in model space. I'd be really interested. Machine learning and model emulators have come up a few times. Other ways we can map that very, very quickly. Could we build a kind of mock-up system?
I think that's worth looking into further. I mean, from what I was taking from your points, you're still thinking about this as very much as satellite activities, having additional forcing data sets available to sort of explore different aspects of forcing uncertainty. And some of the questions which have underpinned the discussions today have been like, well, whether there wants to be some substitution of exploration of sort of initial condition uncertainty to instead explore forcing uncertainty. It's probably, is it worth getting a consensus on whether we think that's just too hard for this round? There's certainly value.
Yes, so I think it is worth exploring, and I think we can take advantage of the emulators to really explore the parameter space in some way there, and perhaps we can then come up with two or three sort of kind of what if type kind of scenarios that we would encourage the groups that want to do it to perform. I sort of think if we do try and give it to everyone to do tons of different ways of doing it, it will get very complex to analyze. But I just think, if we particularly work with the groups that are going to do the huge ensembles, we can perhaps just come up with kind of two things that are coming out of the emulators and kind of coming out of emulators in kind of some way.
Steve?
Sure, and I think we'll, just as context, of course, there's significant uncertainty in anthropogenic forcings as well. I think dealing with the uncertainty in natural forcings is more doable near term because we haven't generated uncertainty data sets for the anthropogenic forcings, but I guess that's just a bit of context. It's definitely on our agenda, but it's really just been a matter of resources. I mean, we've had, steady funding, but steady funding is actually decreasing funding in real dollars. So, it's just not something we've managed to do, but it's something we would like to do, so I think just maybe that's particularly more for the US folks. If somebody can think of a way to generate funding to do some of this, we would love to tackle it. We've got some tools built, but just no resources to really put people on them to exercise those. But that could be maybe a next phase. It looks like the natural forcings and land use are closer or there with uncertainty data sets. Thanks.
Do we have anyone on who's affiliated with a center who does one of the very large ensemble experiments? I'd be interested in sort of feedback on whether those groups who historically focused on large ensemble analysis would be open to expanding the scope of those experiments.
I just want to go back to the point Claire was making before, because I think there are two issues that both needs tackling, but they are different. One is what Paul was mentioning, so multiple forcing for the historical, and there is an element of affordability and complexity in that. Well, you make the call, and nobody picked it up, but it will be really interesting to see whether there is that ambition by the different modeling group. The second point, it was the one I was mostly referring to, and it's about the fact that irrespective of, or almost irrespective of the discussion about the multiple forcing, there is still an issue of discontinuity in the characteristic of the forcing between the present day, the past, and the future. And I think, maybe having multiple forcing will help, but the two don't necessarily need to go together. And it really stands out as a feature in the forcing that we are using, that discontinuity. And I think it will be useful to have a strategy, and possibly a strategy that is in the general guidelines similar for the different forcing.
Lots of hands now. Who was first? Yeah.
Just a direct comment to that the advent of the satellite era is a large discontinuity. It's not the only one in the system. And so any approach needs to kind of also cater to Sentinel-2 at 20-meter resolution, for example, has been another step change.
So pragmatic hat. Part one of this workshop is trying to focus on getting CMIP7 done. And I think this discussion is something that very naturally flows into beyond CMIP7, I think, because it's going to be challenging to do anything like this systematically in the next 5-6 months. But one of the other things that I was going to suggest, I think, is that trying to get a handle on what is the biggest uncertainties might be a good way of actually trying to tackle this, because, I mean, we've got so many targets that are popping up, but how big are they? what are, 0.01 versus 0.1 kind of levels. I mean, Thomas has already started kind of highlighting how different things are. And in UK ASM, which is a pretty sensitive model, what the impact actually is. And I think what would be really useful would be if there's an appetite in the modelling groups to do science, because that's exactly what this is. Can we actually come up with, ranking targets of what is sensitive, and is the sensitivity consistent across, 5, 10, 15 models in the CMIP archive? And then could we then try and prioritise, the funding to try and address the biggest uncertainties from top to bottom? Acknowledging the fact that we actually do have an observing system that we're making an explicit assumption that's going to be there. So, like, pointing out the fact that we've got dependencies, we need to keep our eyes on the observing network that's going to be there to make sure that we've still got observations to make these forcing data sets and to continue to constrain them. So I think we've got a lot of work ahead of us, but we need to be pragmatic about the next 6 months versus longer term.
I just wanted to follow up and echo some of your points about pragmatic and practical for CMIP7. The number of model simulations that can be done for CMIP7, of course, if we had these different data sets to explore uncertainty, yes. But again, it's the cost for every modeling center. And then that also adds to the further uncertainty, because the one thing that we kind of forget, the model diversity, model structural uncertainty that then leads to a diverse set of results, which explaining them and with the different forcing data sets, I don't know how confusing it might get, but maybe for CMIP7, we stick with some agreed upon data sets and protocol that then can lead to further science questions going forward. Steve.
Well, there's three here.
Yeah, just a few comments. Firstly, Carlo, to your question, should there be a common approach? I think perhaps a common framework would be helpful, because the specifics of the different forcing data sets are very different. The volcanic, there is data available in the past, but it's of a different nature and things can be reconstructed. Bio emissions might have to be much more stochastic made up. So and the impacts of these things are different. So I think a common framework would be helpful for thinking about it, even at this stage for CMIP7, and prioritizing, saying, okay, most things it's not, we just have a single forcing and that's it. And my other comment is there's no way that we can sample, all possible combinations of different uncertainties to try and give some sort of PDF of what might happen in the future. And I think it's coming at it again from a sort of seasonal perspective, science perspective, it's much more helpful to have, this is your central projection, and these are some sensitivity studies that show, different directions of uncertainty. And that perhaps is something that is feasible.
Yeah. Yes. Is that a dead? Yeah. Ah, Steve.
Online, yes.
Yeah.
I was just going to comment that this sounds perfect for a regular CMIP MIP experiment. Not fast track, but variability MIP. And then we have one central scenario the best we can for the fast track in the near term. Thanks.
Yeah, I mean, I was actually going to say something similar in response to your point about this not being CMIP7. It's like, this isn't fast track, but this is potentially part of the post fast track strategy, and it might be worth thinking a little bit more about what our sort of wider guidance is for that period, like post AR7 cutoff. Yeah, sure.
Yeah, just to follow up on your comment there, Ben, I was thinking the same thing around fast track versus the community MIPS. And also bearing in mind, I think a lot of the modelling centres aren't going to have their latest and bestest model ready in time for the fast track. So the longer term will provide us with new modelling capability and some, which will be the models really to use to explore this kind of uncertainty variability space. So we shouldn't kind of restrict ourselves to fast track, really.
It was a question really to the data provider teams and to Paul and Vaishali, which is how much mileage is there in just, or how much work would it cost people to just write down what uncertainty information they have right now in their version 0 data sets? Some people do have uncertainty information, some people don't, but it would give us, just right after this meeting, some sort of baseline where we can just start thinking about the problem. I don't want to add work to people's plates, but just this is what we've got right now, version 0 might be interesting.
Yeah, so for the land use data, we have HIDE is an input into our model, and HIDE produces a high and a low. At least they have for previous versions of HIDE. I'm not sure if it's available for HIDE 3.4 yet, but I believe it would be likely to be there. So we use that. And then there are different ways of interpreting historical wood harvest rates by country, and there's like some pretty extreme differences in that, and so we incorporate the wood harvest differences and these HIDE land use differences and create a new version of the data set. A lot of the other parts remain kind of constant. I think there is a question about maybe shifting cultivation as well, like what our rate of turnover for shifting cultivation would be. So we, I wouldn't call it really uncertainty, because it's all very uncertain historical land use, but it's more of a sensitivity study. Like if we change our assumptions about what goes into the data set, this is how sensitive the output would be. So.
And I think that's a really good point. What we mean by uncertainty is also very variable between data sets here.
Yeah, I mean, I think we could write something down that'll give people a sense. You know, it gets bigger as you go back further in time. Probably for greenhouse gases, in the scheme of things, the uncertainty is very small in radiative forcing terms compared to a lot of other stuff. So you're probably not going to notice. It's not going to be like Thomas's stuff where you're going to get 20% of the warming is going to change. You might get 20 thousandths of a percent maybe. So yeah, we can definitely write it down. And that might even be a helpful first step for a bunch of things.
More points at this point?
So we have until, we have 30 more minutes to discuss.
Do you want to prompt, Steve?
Yeah, I was gonna. Steve, do you have something coming up on uncertain quantification of the anthropogenic emissions as well?
Well, I hope so, but yeah, the resources are a little tight, so we keep it on the to-do list.
Okay, thank you. Do we have enough information to answer those two questions that we laid out initially with the pre-industrial control protocol, and then the scenario map, and the second one on the variability, and especially with John's presentation, Michaela's presentation, the question about smoothing out versus not smoothing out. I think Michaela's made a convincing point to have that realism in the ozone forcing, with including QBO, and then providing an additional data set that removes that variability. But what about fires, biomass burning emissions? Do we have a plan on addressing that?
Quick question for fast track, would there be some models with endogenous fires and some without, or would all models be using the provided emissions?
It's looking like some models may have interactive fires. So as you saw from John's presentation, CSM3 may. I don't know if UKESM has plans.
Not for fast track, but we will repeat with UKSM2, which will have the interactive fire capability. So, 6 to 12 months for after.
And I think at GFDL, we are in a similar place as well.
Yeah, so well, have we solved everything? It seems unlikely. I mean, is it worth? Can we then summarize what the forcer by forcer, what the strategy will be for both the PI control and for the scenarios? So where are we? So I mean, so we started with volcanic, right? So I mean, you highlighted that the pre 1850 is a tricky period because 1800 to 1850 was biased or was unrepresentative of the long-term average. So do you have a recommendation, a distilled recommendation of what the PI control level should be based on everything?
Not really. I think it needs to be thought about further. I will just share maybe quickly. I shared another plot in the Google Drive that might give more context, showing the 5 or 6 centuries before 1850. Maybe I can zoom a bit on that. Yeah, so it's just time series of SOD from big eruptions, and then the number is the century average. So, yeah, I think essentially needs more thinking, and I think there are 2 competing questions. One is pick a baseline that's representative of 1850, but the other one is also pick a baseline that wouldn't make it the volcanic forcing level very far from the average expectation in scenario MIP. So for example, if I was to take 7050 to 8050 as a baseline, the mean SAOD would be twice more than the long-term multimillennial average. And I think having that as the base number for scenario concentration might be tricky. So yeah, I think I don't have a plan. I think I need to, I'm always happy to hear more thoughts. I think I need to talk more to the community.
And is it possible to overstate the importance of that period? Like if you've got a PI control where you're exposing the system to that forcing for 1,000 years, is that like overweighting the importance of that potentially quite biased time period?
I think I didn't follow. So you're saying you should do a 1,000-year time?
If your pre-industrial control is conditioned on the forcing between 1800 and 1850, and then
yes,
you sort of how do you balance? How do you walk that tightrope? How do you not overstate the? Do you have a good feeling for to what degree it should affect the long term?
Well, yeah. So like long-term time average volcanic force is going to depend on model, but the average cooling effect is on the order of 0.2 degrees Celsius. So maybe if you pick a time period as a baseline that has a forcing twice larger than that, such as 7050, 8050, you might get an extra 0.2 degrees Celsius cooling in your PI control.
Yeah.
So, not huge, but also not small.
And is there a good do you have a good sense of how long it takes the system to what's the slowest timescale of response to volcanic forcing? I guess that's what I'm getting at.
Well, yeah. I mean, if you're talking deep ocean, I also dropped another link here, but it's like hundreds or thousands of years.
Sure. Yeah. I mean, that's what I'm kind of worrying about, I guess.
Yeah. Well, nobody can see that on our screens, but that's ocean heat content response to Krakatoa in blue, and the title of that paper is Krakatoa lives, because in terms of ocean heat content signature,
it's likely still here today. And so same for sea level rise and yeah. So maybe we're overthinking it, because in a sense, if you wanted to write the 80-50 condition when you talk about ocean, like maybe you need to go back to the 2000 year before.
Yeah, right. Yeah. Right, three more.
Yeah, I was just going to chime in on what Tom was talking about. So the Gleckler paper was the one that you're citing there, and in various phases of CMIP, we've actually had situations, and one of the GFD models actually had this, I think in CMIP7, where the impact of the early volcanic events actually dropped you into a negative ocean heat content, and it literally took the entire historical period to pop back into the positive again. And so like this is actually something that the ocean needs to be considered when you're thinking about volcanics, which is what you just said. But that's a hard problem because it's not something that's going to, calibrate itself in 5 years. It's going to be far longer than that. And there's been some unusual simulations that have had these negative ocean heat contents, for example, but it's not consistent across every single ensemble member too. And so it's difficult to figure out what to do. But I think, yeah, I mean, Jonathan Gregory, again, would be a good guy to sub in on this conversation because he was one of the reasons why the CMIP6 protocol changed. And I do think engaging him in this kind of dialogue would be useful. He'd have some insights for sure.
Mm-hmm.
Yeah, we had this. We had a similar problem in AR6 when we were doing historical and future climate projections in simple climate models. And actually, what starting point do you actually initialize your emulators from? And in the end, what we actually did was to take all available pre-industrial natural forcing, solar and volcanic, which is about 2,500 years at the time, and now it's more like 9,000 years. And actually spin up everything before 1750 with sort of 9,000 years of data. Now, obviously, we can't do that in an ESM, but I'm wondering, is there sort of, can we sort of maybe sort of take a long pre-industrial period, maybe average that as the sort of pre-industrial conditions, with the knowledge that there's probably going to be some warming over the historical period if you're then sort of reducing, say, your volcanic forcing compared to that pre-1850 period?
Yeah, perhaps can I step back just a bit, because perhaps I wasn't here at the beginning, but I did want to understand that the entire idea to come up with a best estimate radiative forcing data set for each constituent. And I think if we do that, if we include kind of variability for volcanoes and kind of solar and biomass aerosol, we ought to try and include it in a consistent way for everything. And perhaps I could confirm that has somehow been agreed. Yeah, okay, good.
I think so, yeah. I mean, the best estimates of the forcings is what we have, and the implementation of the models in the models obviously may vary a little bit depending on what a model is doing with, say, their interactive fires or even volcanic forcings as well, because there might be some models that might want to run with volcanic SO2 emissions, and we haven't even talked about how to specify injection heights for pre-industrial. So this is something that Tom can spend a week discussing and telling us what we should be doing. So yeah, in terms of having that best estimate plus an estimate of, given all these new work and the consideration for uncertainties, there will be a best estimate, and then there will be all these other ranges and
Well,
to
yes.
address.
So I think that's what I'm trying to understand. Does that best estimate, will that always include into annual kind of variability?
For the PI control?
Yeah.
You mean historical or PI control?
Well, for either or
Okay.
both. I just sort of think we ought to try and be consistent across the whole range in the same way, if that makes sense.
I think from my perspective, yes, that the historical for whatever we have as best estimate, we would have that variability if we have that data. And especially over the observational period, this is what our data providers produce. So it's included. The question then is, in terms of the point that John brought up with the biomass burning emissions, and given that the models respond weirdly to that very high variability over the satellite period, that is the question that we want to address and see if there is something that we should be doing to reduce the impact of that very high variability, and maybe not. So
perhaps I'm just going to try and come back to convince you. I sort of think if we do say we want to include this variability in some way, we ought to try and include it in everything. It ought to be in the control, it ought to be in the kind of historic, and it ought to be in the kind of projections. And if we include it for one of the four things, we should also try and include it for the others. I mean, just so we're saying comparability is important, so we are going to consistently have a look at everywhere and everything, or perhaps that is going too far.
I mean, am I right in saying at the moment in the PI control definition there is no variability in any of the forcings, right? So that would be a departure from the way that we think about what that experiment is, which is
it's not quite true. Bernd can correct me, but the only forcing data set that we currently have, Bernd, do you want to chime in about variability in solar?
Well, just a question about my understanding of the PI control. So my understanding is that the PI control is mostly in order to constrain internal variability. So by definition, natural forcing should be set to a constant value, and that is what we understood for the solar forcing, which is easy in this case because 1850 is pretty much at an intermediate solar activity level. So just averaging over a larger time period, we took 2 solar cycles, so 22 years, is very representative and does not make any, or does not lead to problems when stitching or when combining with CMIP simulations, or when going to the future and the historical. But another aspect I wanted to bring in, for us in the generation of the solar forcing, the self-consistency of the data set in terms of avoiding any jumps, not only on a temporal scale, but also in terms of statistical behavior. So temporal and spectral, to say it that way, was of highest importance, such that, for example, we use reconstruction models also to cover the modern period, the satellite period, in order to be sure that we don't introduce any changes in the statistical behaviors at certain moments in the time evolution. Also, just as an example for the solar energetic particles, solar proton events, where data sets of the satellite data sets are only available after the 70s, we are stochastically projecting these data into the past in order to ensure that over the entire period we have a fully self-consistent variability pattern. That was my understanding for how what is the priority for the representation of natural forcing variability. But maybe it is something which should be brought up in a general context for discussion.
Yeah, very interesting comment, Bernd. I think it's ties in well to, I think Piers' proposal on the face of it is a good one, but I think it's actually impossible. And I think you can prove it to yourself by thinking about how you would do this with volcanic. So if you're stuck in the pre-industrial, it's pretty straightforward. You would just spin up and the volcanoes come when the volcanoes come. And then in historical, you run forward and the volcanoes come when the volcanoes come. But for the scenarios, you're stuck because either every single scenario run has a volcano go off in 2040, which doesn't make any sense because suddenly people are looking at Paris Agreement compliance and you get this nice kind of cooling blip in 2040, which makes your life a whole bunch easier. Or you do it stochastic, in which case you can't compare anything anymore. So I think it's just an impossible consistency to get. Unfortunately, I think we're sort of stuck with that. So we're looking for imperfect solutions, I suspect, which is deeply unsatisfying. So in AR6, you have this thing where as you roll off from historical, the volcanic forcing goes back to whatever its background level is. You get this 4/500th of a degree for absolutely no explicable reason. But I think that's just, I don't think it's solvable, unfortunately.
Yeah, just on that, I think it, to me, makes more sense when we're trying to explain and communicate to people to think of the future scenarios as conditional. So conditional on no huge volcanic eruption and with just a sort of background level of volcanism. And so that's the baseline projection. And then you have some separate studies that tell you if there's a big eruption, this is what happens. And I think for communicating to people, that's much easier than trying to have your baseline scenario include some average level of volcanism.
I would agree with that. I would backpedal from it being impossible to being difficult. Right. I mean, we could have 1,000 different. We could have 1,000 different volcanic forcing sets. It wouldn't.
I would say impossible as well.
All right. But that's not actually what I wanted to say originally. So I guess coming back to Piers' original point about whether we should be having. In an ideal world, you would have some sort of variability represented in the control state. There's a question of why we run a control simulation at all. And then somebody, and I can't remember who now, said, we want to have some self-consistent estimate of what the internal variability, natural internal variability of the system is. But if the picture that we get from an unphysically unvarying forcing background, does that actually produce the same covariance structure? It probably doesn't. Now, in terms of detection attribution, where you use that simulation to sort of assess the significance of the response of climate forces, if we think that PI control is biased because it's unrepresentative of any period in the actual history of the planet, then does it actually undermine the point? I'm not necessarily saying we should do this for CMIP7. It's hard, but are we overstating? Are we overstating what the value of this experiment is? Is it if it doesn't actually correspond to this internal variability which lives separately from climate forcing variability? Is this a hypothetical concept which has no real bearing on the real system?
And just to make it even more kind of kind of more complicated, you are going to have some additional kind of variability within the ESMs, just because they do have a bit of a forcing kind of variability within them. So it gets even more kind of complicated, really, doesn't it?
You mean in the emissions-driven ESMs? That, yeah,
that's right. Yeah. So yeah. So perhaps no. Okay. I think I probably said too much.
Well, just to comment as a scientist who's external to the CMIP community, really, it doesn't make much sense to me. It would make much more sense to have a 1,000-year integration with, you know, our best estimate of a realistic forcing for that period, and that's a much more natural spin up. That's a much more natural background for detection attribution. And if you really want to have a control, to me that feels a bit like in the early days of CMIP when you had like the 1% per year CO2 increase. It's a sort of very simplified idealistic thing that you might use to compare models or something, but it doesn't really relate to the sort of the more general scientific type questions. So that's just an external perspective.
I mean, that's a big suggestion, right? So, like, should everybody be running a last millennium simulation instead of a PI control? That's what you're saying, right?
But additionally, if we had to consider more pragmatic, you know, model issues and whatnot, what would your recommendations be in that case? I mean, I think the decisions that were made for CMIP6, to me, it seems like that protocol somehow holds. We could potentially discuss as to, you know, what mean volcanic forcing we might want to use, but other than that, in terms of, you know, running for say 500 years or something, and then specifying that forcing might work.
Well, I guess, again, a little bit external, so I don't know all the full history of this, but if the idea is to have a control where you deliberately suppress variability, well, then immediately you have the question, well, what about sort of full system models? You know, you can, are you going to suppress variability in aerosols, suppress variability in forest fires? And you can choose to do that, and you might learn things from that, but then, you know, you just have to think about, you know, what you're doing and why.
Right, so maybe not the right time to ask this question, but I was going to take the other end of the spectrum. So Tim was talking about the millennium run, and I was going to end on the other end of the historical, which was the near real time we touched upon yesterday. So in your slide you were talking about 2021 for the switchover, and I was wondering what is the appetite to move that or to update that. I mean, I'm always going to the same point, but that's, and this links to the discussion we had yesterday that was triggered, I think, by Gavin about the relevance of the recent forcing for the general discourse on climate. And so what is the status of the discussion in that respect, and whether there is an appetite to have a moving switch over between historical and scenario. 8 minutes, oh, 7 now.
Is that on this, or does anybody want to comment on that?
So John was asking, is the expectation that we'll do the same averaging as in CMIP6 unless something different is decided in the next 15 minutes? I responded saying that we'll come back to him and the CMIP core panel with our recommendations after we've kind of absorbed all the discussions that we've had so far, and make that recommendation. Is that?
I was just going to poke the bear and say, if we really do care about the climate system being in a stable state, then we've got to think about deep ocean drift, which is something that's not really thought about very much. And so 1,000 years is not going to cut it when you want to try and actually have a model that's got its entire system in equilibrium. So it's one of the things that we don't talk about very much, but it's one of the motivations for the PI control baseline volcanic, for example, because the ocean is a very, very long time scale and drift is a major issue in CMIP6 and it will be in CMIP7. And you've got ESM variability on top of that as well. So we're making ourselves, it's challenging to try and decipher what is forced and what is, the model that's not in equilibrium.
I was going to say the same thing, actually. So if you did have a protocol which involved a last millennium simulation, that would have to be as well as the PI control, not instead of.
Chris, how long did you have to run your ESM? Oh, sorry. Yeah. How long did you have to run your simple emulator to reach steady state?
Well, actually, that's not an experiment we actually ran because everything was done really quickly, as you know from the IPCC process. But I ran it for 9,000 years. The solar time series went back 9,000 years. The volcanic went 2,500. So we just ran that everything before 1750, and then scenarios started in 1750. Which is of course
even historical and then
Yeah.
scenarios, right?
Yeah.
Okay.
Yeah, you've also got to keep in mind for this class of models, most of them have like just a time scale that they stick in there. And so if you put some perturbation in that's kind of going along your long time scales, like got an e-folding time of, I don't know, 1,000 years, but some maybe short of 500. So I don't know how many e-folding times do you want? There's your answer. And on a laptop, you're probably looking at with I don't know, 3 seconds, then you're stable.
I think we have a lot of information, very useful information that will help us figure out what our PIA protocol would be. So thank you for all that discussion and presentations and all that information that you shared.
So just a quick question, when will you be taking it to the core panel? When will the recommend?
Right after the meeting, once Paul and I have. Sorry, right after the meeting, and once Paul and I have had time to absorb, and also,
So by the end of the year, we could just as a generous.
generous, yes, but hopefully before. Yeah.
Okay, before the states, yes.
Well, at the same time.
Probably for the paper.
So the comment that I'd make is, as the data sets are being finalised, we need to come up with a protocol for using them. So I think that actually makes sense to me. I don't know if anyone's got a more sensible statement to make. Gavin, did you want to speak?
So his comment. Okay, Pierce, you already agreed. The conversation, so from Gavin, the conversation is quite limited since once you include ice sheets, soil carbon, interactive dust, fires, vegetation, orbital forcing, there is no clean pre-industrial period and no completeness in terms of forcings. Fair point. But we have to make progress, right? Yeah. So. Right. Okay. Shall we end?
Yep. Thank you very much.
Thank you.